Pending? What does that mean? Oh, it's like it started.
Yeah.
Understood. Thank you, teams, for making it more confusing than it needs to be. Where the hell? Okay. So the consensus from the like really crude poll I put in chat was that you guys want to know more about the battery pack, and the circuitry that is within the battery pack and all that. A little more than motor control right now, which is, I have to say, new for this year. Most people want to know how motors spin first, but this is just as important, if not more. Project, please. Duplicate. Yes, sir. So this is going to be fairly in-depth. I cover like Ohm's law basically, and then build on that equation to show you how the battery pack is spec'd. And then I get into specific parts. These parts are pretty common across the automotive industry, I'd say. So this is transferable knowledge for sure. The law of the land. Really, if you're an ME, the one law that you kind of just need to know and will get you by in most electromechanical disciplines. V equals IR. This is Ohm's law. Voltage is the product, current, and resistance. Pretty simple. This starts to get a little more complex when you introduce a derivative for current, or you start integrating like things like thicknesses to get resistance for various things. But this equation will carry you pretty much all the way to designing a full battery pack. So to go over what these quantities actually are, voltage, current, and resistance. Voltage is electric potential, and you can think of it as pressure or force, let's say in like a fluid system. So if you have a water tower, you have gravitational potential energy built up, and when you let the water out of the water tower, the water flows down the potential gradient, let's call it, and generates energy. The same goes for hydroelectric dams and things like that. So voltage is like gravitational potential, but it's electric potential or electrostatic potential. Voltage can be stored chemically in the form of batteries. Batteries are basically an electrolyte and a separator. So you have electrons flowing across the separator boundary in various arrangements, and that that is how the voltage do. So it can be stored chemically. It can be stored by devices called capacitors. That's basically two charged plates. That's something called a dielectric. This allows for flow of the electrons across the dielectric, but in a controlled fashion. Capacitors, you can almost think of like springs or dampers in electronics or circuits, but that's beyond the scope of this class. So you can store them in capacitors. You can store voltage in capacitors, excuse me. You can store voltage in batteries, and you can induct voltage through coils. Generators work by inducting a current, more current than a voltage, but inducting an electric potential in metal, basically. You move a magnet across a coil. You move a permanent magnet rotor within a motor assembly. You're inducting a current. You're creating a voltage. That's voltage. Current is the velocity of electrons in a conductor. It's analogous to flow rate if you think about a fluid system. It's given in units of amps. And voltage, by the way, is given in units of volts. Voltage is given in volts. Current is given in amps. It is simply the velocity of electrons flowing through a given conductor. Resistance is a little like head loss. So when you have fluid flowing through a pipe, you have frictional effects in the pipe. You have pressure drops from certain devices in the pipe. Resistance is a little like that, in the sense that it resists the flow of current. It resists the flow of electrons. And the units of resistance are ohms. Oh,
Got that like little picture that usually show for that?
no, I don't think so. Where did I put that there? This is maybe made a year ago, by the way. This presentation's off the cuff. So this is a fairly up-to-date diagram of our powertrain. I will go through just kind of basic parts here. So we have the inverter you see here at the very top, on top of a subframe. Subframe sits on top of the battery pack, which is massive. You can see it like basically straps the whole car together. There are 6 battery modules, a load of cooling fans, and a load of control circuitry inside of the battery pack. And it functions as a structural member as well as the thing that stores all the energy, right? We also have a motor back here. This is the MREX 228 that some of you helped pull out last Thursday. The driveline for KS2E is virtually the same as the driveline for KS1E. It's a simple small sprocket to large sprocket arrangement. We have a much smaller spool on this car because of how things are packaged in the back, but pretty much the same driveline setup, pretty much the same motor fixturing as KS1E. So motor, inverter, battery pack. Can anyone tell me what the inverter does? Yeah. That's right. That's right. And it does so in a controlled fashion, which I believe is termed commutation. So when you hear commutation in reference to motors, it's essentially how the current is timed to like energize the coils in the motor so that the magnetic field that is caused by energizing these coils pushes the rotor inside the motor around. In our case, the MRAX is constructed such that the whole body is the rotor. So like the whole damn thing spins. It's not like your usual electric motor where just like a spindle or a small rotor, the whole thing spins. And that's because it's an aircraft motor. It's originally designed for aircraft. So we have inverter, we have battery pack, we have motor, we have a driveline that was designed by the EV powertrain, but that will soon be shifting probably to vehicle dynamics somewhere in the near future. We have those components, and we also have a cooling system. So we need to cool all our components. We need to cool the battery pack, inverter, and motor. The motor and inverter are on a liquid cooling circuit in parallel, meaning that the fluid doesn't flow into the inverter, out of the inverter, into the motor, out of the motor. There's a branch in the cooling conduit so that you're not like co-heating the motor with the inverter. Does that make any sense? Yeah. So we have a cooling system. This is a reservoir here for it. The CAD model is kind of doo-doo, but it's come along since, for sure. I've seen a better model of this in the KS2E assembly. So liquid cooling circuit for the inverter and motor. We have air cooling for the battery pack, which I'll show in a little more detail later. But we have 12 cooling fans, delta fans in the battery pack, 2 per module. Those just suck up air from the bottom side of the car and throw it out the top. That's why you see this grating in the battery pack. Battery pack here is to evacuate the air. Any questions so far? Yeah.
What's the temperature that you want your batteries?
So as per the rules, the batteries, meaning every battery cell has to stay between 45 Celsius and 60 Celsius. And this is actually a pretty happy range for the cells to like discharge at anyway, right? 60C for reference, like across engineering is like too hot to touch. 60C is too hot to touch, and above 60C, your cells start to get toasty. Thermal runaway is the word for the state they're in at that point. So 45 to 60C. If you get cooler than 45C, they actually discharge less. So there's actually a happy sort of amount of heat that the cells want to stay at. We're just aiming we're just aiming between 45 and 60C.
So what makes air cooling for the battery pack better than liquid cooling?
So objectively speaking, it's lighter. It's more feasible in its construction. It is possibly a more available source of cooling fluid, but it comes with other challenges or other caveats in that it's not insulated from its environment. A lot of cars that went to Nevada, a lot of EVs failed pretty miserably because the air outside of the car was 120 degrees Fahrenheit. And if you're trying to cool a battery pack with air that is already very hot, you're in a sticky situation. Liquid cooling would require some kind of fluid conduit, either along the like cylindrical surface of the cells or the ends of the cells. That's very ungainly, or it was very ungainly when we like conceptualized it at first. So feasibility is like the primary driving factor, I'd say, in air cooling.
Air cooling, you can get a more consistent cooling across the cells, whereas with liquid cooling, if you just did them at the ends, you get the batteries cool at the ends of the cells, but towards the middle, it kind of a bit hard, which kind of.
Well, I wouldn't even say that. I would say end cooling is about as effective as surface cooling for cells. It's just very difficult to do as far as like electrical insulation goes. Because if you're trying to cool a surface at which electricity is also being conducted, that's a lot of like, I don't know, it's a lot of precision that we frankly haven't like mastered yet. So yeah, good question. There's a lot of trade-offs there, mainly weight and feasibility. Any more questions on this? Cool. So here are a bunch of system specs on the battery pack. There are a lot of parameters of interest when it comes to the battery pack. Our chief parameter of interest is energy. We specifically spec'd out this battery pack to 8.3 kilowatt hours, which is a lot more than a lot of other FSA EVs, because we wanted the case to be the complete endurance, no matter what. That's pretty much why it has 8.3 kilowatt hours versus the 6.3, 5.2, 7.1 that you see in a lot of other FSA electric cars. So energy was key in speccing out and configuring this battery pack. The system efficiency is actually 80.3%, and this comes from multiplying the efficiency of the motor, which is 95%, the efficiency of the inverter, which is 95%, and the efficiency of the battery pack, which accounts for the thermal losses that you get during power draw, during cell heating, basically. You see the individual efficiencies listed there for motor, inverter, and battery. And yeah, as I said previously, system efficiency is just a product of those three values. So the way that energy is computed is we take the capacity of each parallel string of cells, which is 4,000 milliamp hours times 6, 24 amp hours, and we multiply that by the system voltage. So 24 amp hours, the battery pack capacity, times the 400 volts, I believe gets us to 8.3 kilowatt hours. Is how that, I believe how that computation is done. Ooh, I'm talking ahead of myself here. But anyway, that's how we compute energy, is the system voltage times the battery pack capacity. So we spec this battery pack to put out 80 kilowatts at peak. 80 kilowatts is by no means the continuous power draw of the car. Mostly because in any racing event, we don't need that much power. But it is a good thing to hit your peak power, because it makes sure that at whatever power below that, whatever power you draw below that, that you're at. Sorry guys, really tired. Make sure that you don't get too hot, basically. Make sure that your system isn't overstressed, is why we spec it to 80 kilowatt. Also to saturate the power limit to see what would happen. So I say the max system current there is 288 amps because when you draw power from any battery cell, the voltage will actually sag. So if the voltage sags, the current discharge from any battery pack or any battery cell has to rise up to meet it. So let's say the voltage sags to 2.5, that times like 96. If you take that quantity, 2.5 times 96, and you take 80 kilowatts and you divide that quantity. Sorry, this is a harebrained explanation. I really should have done this in like line math instead of just a table. But anyway, take 80 kilowatts and divide it by the sag voltage, you get 288 amps of current draw, which is, much higher than what we usually say is the nominal system current. So, like I said before,
right quick, to actually give you the answer on how we got the capacity of the battery pack, the energy. What that was a calculation from what we could actually draw from the battery. So we actually did battery testing about 1.5 years ago. Well, actually, no, it's close to 2 years now. And what we got from that battery testing was that we could only pull about 20.75 amp hours from the cells between the ranges that we actually wanted to use them in, which is about 4 volts to 3 volts. Doing that, you times that by what we actually want our voltage to be, which is a 400 volt system, you get the 8.3 kilowatt hour figure.
Yep.
It's not 24 by 400, it's 20.75 by 400. That gives you 8.3 kilowatt hours.
Gotcha. Yeah. Thanks for that catch. Yeah, we actually did a lot of cell testing to determine like what type of cells we'd use in the first place. So we looked at our old like prismatic pouch type cells, the lithium polymers. We looked at the cylindrical cells we're trying to run now, and we looked at some like Lumineers, like drone prismatic battery cells as well. The Lumineer cells were like very sketchy, they got pretty hot. The tabs got very hot in testing. It didn't seem to be constructed all that well. But above and beyond that, they didn't actually put out the energy that they said they would. So it's a good thing we cell tested, because if we'd gone in blind and trusted the like energy figure that the manufacturer set, we'd be in big trouble. Like it only put out like 60% of the energy they said they had. So yeah, cell testing is a must. Very important.
It also burned me. I actually still have the burn mark on my wrist.
Okay, yeah, that's why he has a beef with those cells in particular, is because it literally burned him. I know that now.
Yeah.
Cool.
Yeah, it was crazy.
Yeah.
So how did y'all do cell tests?
So we have this this instrument called a CBA, computerized battery analyzer. Unsure how it works really, but some microcontroller and some data acquisition device that discharges the current from the batteries in a controlled fashion. Like you can tell it to like cycle discharge. You can tell it to discharge just maximum, so you can see like the drop over time in energy. But yeah, it's a specific like set of equipment we use. As far as like contacting the cell and everything, we literally took like copper wire and just like jerry rigged it with like a C-clamp and stuff and stuck some cables to it. So yeah, that part of it was kind of like ratchet, but the CBA was a good buy. Let us verify all the cells. So this slide explains how we got our target current and target voltage. So the competition limit, as you guys know, is 80 kilowatts. And that power, 80 kilowatts, is the product of voltage and current. Or, as per Ohm's law, also the product of I squared, current squared, times the resistance of the battery pack. So the maximum continuous current through the inverter is 200 amps. Dividing 80 kilowatts by 200 amps gets you 400 volts system voltage. So when we started designing the KS2E, we actually picked the inverter first. This was coming off like the old Bamo car inverter on the KS1E, just like crapping out, failing, just cutting out the car due to interference. The inverter selection we have now was born of like shopping for inverters, doing like a decision matrix, and making sure it like fits within our cost cap and our power level and everything. So 200 amps was the maximum continuous power draw. We figured we'd spec the system, define the whole system based on that 200 amp 200 amp continuous power draw. So that's why the system is 400 volts, is because the maximum current output of the inverter is 200 amps. Any questions so far? So I think this is what Des caught earlier, was the pack energy calculation. So when we went to spec our parallel number of cells, the number of cells in parallel, what we first did was we did a bunch of lap simulations. We gave this software called, what's it called, Optimum G. Gave Optimum G basically an old 2019 endurance track, and we set the car to do like 1 lap. And the energy energy expended in 1 lap, we multiplied by 14 or whatever, or however many laps of endurance we had. And we got like the amount of energy that we need to complete endurance. I believe that was 7.5 kilowatt hours was the amount of energy to complete 14 laps of this endurance track we gave Optimum G. So we divided this 7.5 kilowatt hours by the system voltage that we previously determined from selecting the inverter, dividing the power limit by the inverter current. We divided the 7.5 kilowatt hour figure by the system voltage and got the capacity. So now we know the capacity, we know each individual cell's capacity. We just have to divide this system capacity by each individual cell's capacity. We wind up with 6 parallel cells, 96 series cells. So does anyone know how many cells that is total? 6 in parallel, 96 series. So 96 sets of 6 parallel cells gets you 576 cells. That's right. These slides are cancer. I'll be straight up. Hard recycling these. Anyway, I think I just explained how we got the cell capacity figure. I think I explained how we got the system voltage. So all you should really take away from this slide is that capacity, that's the amp hour number for each cell, as well as current. They sum in parallel, whereas voltage sums in series. To further comment on how we configure the battery pack as a whole, we have 6 modules, right? We have 6 modules because there is a rule that says you can have no more than 6 megajoules in each compartment of a battery pack. So what we did to get this 6 module figure is divide 7.5 kilowatt hours by 6 megajoules, whatever the converted kilowatt hour to megajoule value is. From that computation you get 6 modules. So that's why we have 6 separate compartments. That's why we have 6 modules. All right, here's a module. I showed you this last week and went into a decent amount of detail. This is a way more updated model, which actually shows the fused bus bar models that we'll be using on the actual car, including the separator layer that those sit on, and all the other bits and bobs that go into the battery module. Any questions like off the bat about the battery module and how it's constructed before I launch into a lot more detail about it? Yeah.
So are you gonna make extra packs like this just in case one of them goes bad?
So these are really hard to get together in the first place. I don't think we're gonna make extras. I think we have, I don't even know if we have enough cells for an extra module. We do not. So
We have enough cells basically to test them, and we fucked any of them like up during testing, but that's about it.
yeah, we have like a fuck up margin as far as how many cells we have, but we don't have enough for a whole nother module.
Yeah.
Yep. So like I said before, the electrical configuration of these cells in the module is 6 parallel 16S. And that sums over 6 modules to 96 series cells throughout the entire battery pack. I mentioned why we have this sort of like this module compartmentalization. It's because of the 6 megajoule limit per accumulator compartment. I haven't gone into detail on thermistors and how they work. So does anyone know what a thermistor is? It's right there. Hell yeah. So we have, I think, 7 thermistors per module. 4 on this side and 3 on the other. They sit in these little pockets in the plexiglass and are just screwed into the bus bars. And they measure the temps near the battery cells, near the cathode or anode of the battery cells. So in the rules, there is some stipulation that says you can either directly measure the cathode or anode of the cells, or you can be like 10 millimeters away and measure the temperature of the bus bar, because the temperature of the bus bar is pretty close to the temperature of either the cathode or anode of a cell. You guys know what I mean by cathode or anode, by the way? Cathode is the positive side of the cell, anode is the negative side. And they're just like the ends. The cathode is like a little button, you know, it's all fancy. The anode is just like a surface. Nothing fancy about it. We have thermistors in the battery pack to make sure that the batteries don't get too hot. To make sure, as we said before, to keep them between 45C and 60C. Yeah, next point. The bus bars you see here are going to be made of either nickel or copper. We haven't decided yet. And they're fused. You see this like little neck here? That is the fused bit of the bus bar. Too much current goes through that, the piece of metal literally melts. These bus bars sit on top of this GPO3 separator layer. GPO3 is just like a fiberglass or whatever that's rated for our temps. That's why it's special fiberglass, not some generic shit. Okay. Bus bars sit on top of the separator layer, and these buttons sort of like fold down to then be spot welded to either the cathode or anode of each cell. Structurally speaking, the module is made of a bunch of HDPE retaining plates. The end blocks are HDPE, as well as the retaining plates that the cells socket into. Really simple construction there, like a couple of brass heat set inserts, screws really, and a bunch of standoffs as well. Moving on, we have cooling fans, as mentioned previously. This duct has since been redesigned, and I think what we're gonna do in some of our projects is actually have someone play around with slicer settings and make sure that duct like comes out okay. Because I did like one print of the fan duct and it was horrible, looked really noodly. But it kind of has to be 3D printed. It can't be milled, can't be laid up. So yeah, we have to make sure we nail that surface, because honestly, you lose more pressure to friction in the duct like this than you do to like the actual surfacing inside and all the CFD you do to determine that surfacing.
Do we have material that's rated?
Oh yeah, this is all rated to.
Well, I mean 3D.
Yeah, ABS will do it. Yep.
Why can't it be laid up?
Why can't it be laid up? I believe it's because there's like a contraction, like on the front side, if you see that, there's a contraction to the duct, and the rest of the surface is kind of like convex, I guess. Anyway, you have concave and convex geometry that makes it to where you can't release it from a mold, basically. So if you put this in a mold, you like it would never release. It'd just be like stuck in the mold. That's why we kind of lay it up. Other parts of the battery module, we have connectors. We call them AMS connectors or accumulator management system connectors. Those take the thermistor signals and the 16 voltage signals. That's the 16 voltage measurement per bus bar. Those sort of put them all in one place at the connectors, and they send it out to the AMS, the accumulator management system. So all this cabling is wired into those connectors up at the top there. Last couple parts, we have these like nubbins on the end. They're just like the positive and negative ends of the modules. They are special like slip fit connectors. They're extremely expensive. They sort of thread into bus bars at the top of each end plate, which you can see are routed down to the cells here. Those pegs, those snap plug connectors have sheaths. They have to have sheaths. You can't just have like 200 amps uninsulated at the end of each module. So they have these like special 3D printed sheaths. You haven't really nailed the design of those down. They're kind of wonky looking if you look at them. They had to be printed in 2 parts when we like prototyped them, but yeah, maybe for someone else to redesign. Any questions on module? Yeah, so as I said before, our bus bars are fused. Anyone not understand what a fuse is? You all understand what a fuse is. Current gets too high, metal melts. This just gives you a better view of like the bus bars in the module. The bus bar sitting on top of the fiberglass layer, which sits on top of these like Delrin plates or HDPE plates. And this was meant to be shown as sort of depressed down and spot weld to the ends of each cell, but I got really lazy and didn't really want to do the sheet metal modeling for that. So yeah. The bend is accounted for by the length of the neck, though. There is extra length so that the little buttons can bend down and touch either side of the cell. So worry not. So as I mentioned before, the battery pack is as much a structural member as it is a energy storage device. We have these pretty chonky mounts which fasten the battery pack to the chassis. We call these the chassis side mounts and these the accumulator side mounts. Bailey has actually since designed new accumulator side mounts. These are out of date. But yeah, that's how the battery pack interfaces to the chassis and mounts to it. There are 8 of these in total, and they kind of just weld to the outer shell of the battery pack. The outer shell of the battery pack is 90 thou aluminum, 7075, I believe. It's all bent and welded together, as few bolted connections as possible in this like battery pack shell because we want to keep the weight friggin' low. And this is honestly probably a more structurally sound way of doing it, welding it all together than bolting it all together. Other notable things, the floor has this hole pattern in it. It's a hexagonal hole pattern. This is done for airflow. Like I said before, the cooling fans suck air up from underneath the battery pack and throw it out the top. So you need some grate at the bottom. That's why we have this hole pattern. There's actually more to this hole pattern than you'd think there'd be. There's some like international standard on like grates, right, for HVAC people. I use that standard to make sure that the pressure drop was minimal at the floor, and that's how this like hexagonal hole pattern geometry came about for the floor of the battery pack. The modules are just bolted in by 1/4-20 bolts. So there's 2 on each side of the battery pack. Excuse me, there's 2 sets of 1/4-20s on each side of the battery pack. There's 2 sets on the underside that bolt up into the floor and then up into the module. More view of the structure here. This is a much better view, honestly. So this shows you the shell of the accumulator. Again, all 90 thou, 60 thou or 90 thou? Yeah, all 90 thou aluminum, sort of tab slotted together and socketed together and then welded up to these separator plates. There are 5 total, as I said before, we have 6 compartments. This construction was like the easiest way to like arrange 6 modules abreast. And to contain it structurally sound as possible. Other features of interest, there's little notches in these separator plates that the cabling can go through. And we have like a little bit of a divot in the top of each separator plate so that you can drape wiring over it, because we're gonna have like, how many signals total? 16 voltage signals plus 7, 23 individual cables coming out of each module that then have to be wired into the lid of the accumulator. So as load of wiring within the battery pack itself. That's a cool little top down, shows you the shows you how the modules are like connected across in series, so it's like all one big circuit. So these 2 ends are the outputs of the battery pack, essentially, of the module set, let's call it. But you'll see that these sort of like snake in their arrangement to create a series circuit of 96 cells effectively. So I myself couldn't like visualize this like really solidly when I started designing this, or at least learning about it. But now I have this for you, so you're much less confused than I was starting out. Any questions? So, the design of this cooling duct was pretty non-trivial, I'd say. I iterated on a couple things, those being the like curvature of the surface sweep you see there, as well as the like width and diameter of the openings. I iterated those across a bunch of like flow sims to get basically maximum pressure at the inlet of the duct. So this is like a cool sort of visualization of the flow sim that I did on the battery pack. As you can tell, like the flow is pretty constant. There is not a lot of like turbulence through it. It's fairly laminar. It's gets up to, I think, let's see, 10 meters per second, which is pretty fast, and pretty expected, honestly, for how powerful these damn fans are. So it checked out in simulation on cooling, and we expect we'll actually be expending too much power cooling the battery pack since we have so many fans. This arrangement of cells, by the way, this like hexagonal arrangement is like the best for cooling. This is like also used in heat exchangers and two bank condensers and things like that. So this is like a pretty standard arrangement for something you want to cool. Any questions on this? Yeah.
Is there any way to add pins to the batteries, or that not allowed?
Oh wow, you're like way ahead of the curve. Yeah, that's possible. We talked about actually doing that for like each set of 2. If this CFD didn't work out. But yeah, you're allowed to. You just add like so much hardware, so much weight to the battery pack. Yeah. Yes, I made this slide because I got frustrated at people asking like which way the cooling goes. Sucks up from the bottom and blows up the top. I've since thought that it doesn't really matter which way it does that. I haven't like simulated the reverse scenario in which these fans are pushing air into the modules, but I reckon it's enough cooling. Honestly, there's so much overhead with the velocity we're cooling at that it could possibly be okay. But yeah, for now and for all time, please understand that comes into the bottom and is thrown at the top. So
Let's see if anybody's really dug into the rules. What could be the problem here if here with sucking air from the bottom?
Well, I don't know if this is a rules thing, but it'll pull stuff up because like there's like the skid, like you can get stuff in there like dust and stuff, and it'll pull it through the whole system.
That's a valid concern. Not a rules question.
So basically, you're not allowed to have an underside fan that would pull the car closer to the ground to increase downforce.
Ding, ding, ding.
Theoretically, it could be looked at some way as to be creating more downforce instead of just a school.
Exactly. Now,
Ding, ding, ding.
You put something underneath it by a couple of inches, like the plate on the bottom of the car.
Yep. That's it.
under tray.
Understand, that's the word.
Yep.
Yeah, we have an under tray, so they can't accuse us of blown arrow or whatever.
Yeah.
But the rules honestly around that are like a little bit vague. Like they make allowances for cooling, and you'll see a lot of teams like put their radiator fans on the back. Like I don't know how appreciable effect that has, but okay. But yeah, blown arrow bad for some reason. No fan car, sad. You had a question.
You said earlier that sometimes the air close to the ground is super hot. So would it be worth it to think about pulling air from higher off the ground?
Yeah, absolutely. We talked about some kind of louvering or ducting made of carbon fiber that would like pull air in, basically as a ram air intake from the side of the car or the top. But we were so committed to like this construction of the battery pack that would be completely infeasible. Like you'd have to like rearrange the entire battery pack to make some kind of louver or ram air work. But that's been done and is honestly pretty smart. So whoever redesigns this, and hopefully they use my modules, not mine, in case you say these modules, whoever redesigns this should really, first of all, design it out of composites, carbon fiber, so it's not heavy. And second of all, try to make a louver system like that work. Especially because you can only really need like 4 fans to cool this. You don't need all 12. Yeah.
Is there a way to like cool the air that's going into it instead of like?
So on the combustion car, I think they honestly talked about like a Peltier cooler. That's like
Wait, hold on. Someone used my idea. Ain't no way.
I don't know what you're talking about.
I was the one who suggested that, putting a Peltier on there.
So I don't think, do you know what Peltier device is?
Not really.
So I don't even actually know how it works. But basically you power it and it gets cold. Like it's an electrical device that like sucks the heat out of the air and other things. Honestly, I have no idea how that works.
It works like a fridge or like.
It's not circulating refrigerant is the thing. It's not like moving fluid to like dissipate heat. Window.
Trying to figure out how to explain it.
It uses thermoelectric cooling.
Oh. Wait, what? So this is what they look like, first of all. Yeah. Semiconductor.
Yeah, it's basically a semiconductor effect. You run current through something, and how do I explain it?
Even Des doesn't understand how like.
No, I understand it, but I'm trying to figure out a way to explain it without explaining semiconductors to you.
Oh, is there a way to cool the air coming into the battery pack? I don't think so. Dry ice. Literally dry ice.
I mean, yeah, that's another thing. Teams were actually putting dry ice into their water, if I remember correctly, at Nevada.
Yeah. Yeah, I think a lot of teams who were running liquid cooling in competition were putting like ice or dry ice right into their.
Yeah,
Oh yeah.
yeah, that's what she said.
Yeah, just looking at.
Oh, that's not ungainly or dangerous at all. It's like
Yeah.
excess electrons, while the p-type have a deficit of electrons.
Great.
So, no. Using the battery pack to power Peltier coolers to cool the battery pack is ass backwards and inefficient.
It's very inefficient. Those things they're like 30% efficient at the most, and you're paying like $500-600 for a Peltier that can pull 30% efficiency.
The thing is, if you're passing air fast enough in high enough volumes, it doesn't cool appreciably, right? Like you have to have a certain amount of interface area for a certain amount of time as well to learn heat transfer for it to cool effectively. So not really feasible for our application.
Do you have to worry about liquids going in from the undertray, or do you not have to worry about, like, if it's raining, let's say,
So
Yes.
would it pick up water? Is your concern?
we've basically whiffed on like actually integrating some kind of filter into this. So if anyone has ideas, I'm game. Yeah, slap some like PC, air filters or whatever on the bottom.
You can, you know that hydrophobic fabrics you put over the top of a regular air filter, you just put that across the bottom. And the air comes through.
How expensive?
What?
Yeah.
They're not that expensive. Hydrophobic fabric.
Yeah. All right. So this is the HV enclosure. This is where all the control circuitry, safety circuitry, and monitoring circuitry, let's say, of the car is housed. So there are a couple components that I'll point out, and then we'll get into greater detail on a bunch of other slides. What time is it?
7:23.
Okay. I think we'll run till like 7:45, and then you guys can maybe cut me off. So
does this run off like an Arduino?
No.
no.
Well, no.
So there's a teensy in the VCU, which is the vehicle control unit, but that's a completely different board circuit, not in the battery pack. In the battery pack, though, we have a couple of items. We have the accumulator management system, which, as I said before, but maybe didn't explain completely, takes all the voltage signals from across the battery pack, all the thermistor signals, and it turns that into CAN bus, which is a digital signaling protocol. All the thermistor and voltage signals are analog, right? This takes all those like 96 signals, or however many it was, 21 times 6, right? It turns that into 2 pins rather than 96. So it can report that to the VCU, and the VCU can decide what to do with that information. If a battery cell gets too hot, the VCU shuts the car down. If the battery cell is too low in voltage, the VCU shuts the car down. If a fuse blows, the VCU shuts the car down. And that reporting or data acquisition to the VCU is managed by the accumulator management system.
Most of anything is to anything. VCU shuts the car.
Right. Yeah. Anything goes wrong, the VCU shuts the car down. Yeah.
So if a fuse goes off, what happens to that entire bar? Because it's all one piece, right?
Yeah.
So that's the point.
Yeah.
Each cell is fused.
Each cell is fused, so would you have to replace that entire bar?
Yep.
One cell is-
Yeah.
That whole bus bar, yeah. So there was actually a lot of debate on how the hell we manage the car knowing if a fuse has blown, because it's too quick an event, like it's on the order of milliseconds. It's too quick an event usually to just detect by like a thermistor. Most temperature sensors have too slow a response time. The voltage, however, does not. The voltage you register is usually really fucking low when you're only pulling from 5 cells in parallel versus 6. So if the car, or rather, if the AMS sees that a string of cells is pulling really low, then it's almost sure that a fuse is blown. So that's how that air handling is managed when a fuse blows.
So what happens if your batteries get too low? Like, does it just not turn on? Or
What do you mean
how
too
do
low?
your batteries manage to go?
So
Inside of the BMS, we can set the parameters ourselves to what we want to turn it off at. So for instance, if it reads that the battery voltage hits 3 volts, we can say, hey, turn off. Like just turn the pack off. You can do that.
it's a program cutoff. So the cells themselves don't like shut off if they're drawing too much power, or if the voltage in them gets too low. If you like short a cell to itself, it'll just like it'll just catch fire and like explode. So yeah, it's a program. It's like a controlled thing. We set a floor voltage, basically, is what we call it, when we're programming the AMS. And if any cell hits that at any point, the car shuts down. Okay. We call it the AMS because it combines a thermistor sensing board as well as the BMS, which is the battery management system. That's both of those things. This is both of those things in one enclosure. Moving on. We have a bunch of connector banks. That's just for like checking voltages of the entire pack and all the like signaling that has to go to the VCU and so on. This connector bank in particular is 12-volt power out from the car. And that 12-volt power comes from a DC-DC converter. The DC-DC converter basically takes the 400 volts of power from the battery pack and turns it down into 12 volts. It's basically a solid-state transformer, as I understand it. Maybe Des can correct me on that. That's what a DC-DC converter does. That's where we get 12-volt power.
It's close enough of an approximation to what you can say. It's technically speaking, what you would call is a switch mode power supply. It uses a transistor and does magic with a digital signal to lower or raise the voltage. In our case, it lowers the voltage.
Right. So this system has kind of since been redesigned. I believe what we're using now is 2 DC-DCs on a plug board. We've also broken out 12-volt power to inside of this because all of these boards run off 12-volt power. So a lot of stuff has been removed over like the last 6 months, let's say. So don't take this from gospel.
That's correct. It has 2 modules on it. One transfers from 400 volts down to 24 volts, and the other transfers from 24 volts to 12 volts.
Right. All right, more parts of the battery pack. These 2 big cylindrical things you see here are relays. Anyone know how a relay works? So a relay is just an electrically actuated switch. If you power the relay, power can flow through it. Meaning, there are 4 pins to this. If you power the 2 pins that are like the relay on pins or relay close pins, the battery pack will flow energy through those bus bars out of the HVD, the high voltage disconnect. That's that big orange thing you see like that I'm pointing to. These relays just manage switching, this on and off switching of the battery pack. So most error handling, the way it works is the VCU will just command the errors to open. The errors are the accumulator isolation relays, those things. So in most events where something goes wrong, those open. Those relays open, power doesn't flow through those. Those are the errors or accumulator isolation relays. We have a bunch of bus bars. These are just like bent copper sheet that conduct electricity. Way better than cable for this use case because you can get into much tighter spaces with it. Don't think it gets as hot, especially because it's an open air here, dissipating heat. And it's just, I don't know, in most cases, it's safer and easier to package than cable within a battery pack. We've covered off on most things here, covered off the connector banks and everything. This is meant to be a fan controller. This box houses a fan controller, but over the last 6 months, we've realized that this fan controller is inadequate, and we've made our own, meaning Des has made his own, and that now has a new home, along this like face of the battery pack, HV enclosure, like over here. Last part, and probably one of the most crucial is the pre-charge discharge circuit. I'm gonna go into detail on a couple other slides, on subsequent slides. So I won't like ambush you with detail just yet. But as I said, pre-charge and discharge basically make sure that you have a slow roll of power, slow roll on of power when the car turns on, and a slow roll off power when the car turns off. So you don't immediately want 400 volts of electric potential present at the DC input to the inverter because it would blow up the capacitors. You want to slow roll that power on by basically shorting some of the power as heat. So what the pre-charge circuit does is that when the car turns on and the shutdown circuit of the car is on, a relay is engaged and a circuit is completed that contacts these big copper bus bars, by the way, such that some of the power in a turn-on event is shorted to a resistor bank. If you short power, if you run power through a resistor bank, they dissipate that power as heat. That's all resistors do, is take power and turn it into heat. The inverse is true of discharge, but we'll get into that on the next page. Yeah, this is a good analogy. These like water analogies honestly get you pretty far in understanding, like on an intuitive level, how electricity works. You don't suddenly want 400 feet of water behind a dam. If you're filling a dam, you want it to be slow. The sudden impulse of like, I don't know, somehow making 400 feet of water exist at a dam would blow up the dam. So you want a slow roll on power, slow roll off power. Discharge. So the discharge circuit, pre-charge circuit, if I haven't mentioned before, are the same board, as is annotated here. The discharge is the inverse of pre-charge. So when the car turns off, when the driver turns the car off, or if we switch the car off at the like master switches, a relay is closed, a different relay is closed, such that power shorts from these bus bars into the resistor bank and is dissipated as heat. You want to do this on the basis mainly of safety. Another interesting thing with discharge is that you can discharge the capacitance in the inverter to the motor actually. We have this air handling with the VCU where, say the HVD, the high voltage disconnect, the output connector of the battery pack is like open. The capacitance in the inverter can still be discharged to the motor. So it's the safest way. Like we've covered off on every scenario of discharge, basically. Did I explain that correctly, Des?
Yeah, so that's actually going to get redesigned a little bit because the way that's handled right now is not good, I guess you could say. The logic behind it anyways, but essentially what you described is what happens. So if the HVD is disconnected, so the battery pack is actually disconnected from the tractor system, you still need a way to discharge the capacitance from the motor controller, the inverter. So what we do is we send a signal to the VCU to then send a signal to the inverter to let it know that it needs to discharge itself. What it then does is it takes that capacitance, that energy that's in the DC link capacitors inside of it, it sends that to the motor, and essentially just vibrates the motor to discharge that little capacitance that it has left.
Will it literally vibrate the motor?
Yeah, so instead of making it spin, it does it laterally. Like it makes it essentially shake.
Okay.
You won't be able to detect it, but that's essentially what it's doing.
Yeah, and this discharge in the motor, by the way, only happens if the output connector to the battery pack is disconnected, basically. Any questions? Yes, sir.
So why don't you want it to turn off immediately? Why can't you just have power off?
So Des, what's the problem with having like capacitance in the DC bus?
Oh, so discharging doesn't work like that. So if you just like open the relays, the capacitance will still be there. Like it's not going to be like pre-charged where if you close the relays, the voltage will instantly rise. Like it has to go somewhere. It's the problem.
Has to
So
go
with
where? So
you have to make that energy go somewhere. So with discharge, you need to have it discharged, as heat. Otherwise, it's just going to be there.
on the basis of safety, because if you disassemble any part of it, um, while a capacitance is there, I imagine you get some kind of arc or just something
Or
dangerous.
like you touch it and it like electrocutes your ass.
Yeah, it'll electrocute your ass. That's right.
Yes.
Maybe it's on itself.
Why can't you just make it arc itself? That's not a real safe way to discharge things.
But it's cool.
Okay, so put it like this. Imagine.
You would lit-
Let me actually do the calculation right quick.
Oh, that's right. Yeah.
So imagine if you took like a Mustang's worth of power, right? And you just like yeeted it through yourself, or like yeeted it through a piece of metal or something. That's what essentially you would be doing.
Instead of yeeting it through random metal, yeet it through like the metal designed to discharge.
Yeah.
Big spark.
What safety?
Marco's just a pyro at heart.
I love it.
If you do that, you may as well.
Flathead screwdriver?
Yeah. Flathead screwdriver.
Yeah.
Okay, so maybe I shouldn't.
Why should never take a fucking old?
Yeah, I shouldn't. I shouldn't. think about that. So I already explained I explained the AMS in detail already. Yeah, I've already said all of this. Aside from the fact that there are 84 thermistor signals actually and 96 voltage signals. So that's 180 cables coming out of the modules, or wires rather.
I see no wrong, kids.
Huh? Yeah. See no evil.
Are they all the same color?
No. So I think we actually have a pinout with like some color indexing. We've tried to get a lot better at that. It used to just be random in the past. But me and Des are a little more on point as far as that organization goes.
Just to correct something right quick.
Right.
Earlier you said that thermistors were slow in their reporting. That's actually not true. So essentially what a thermistor is a resistor designed to be like very sensitive to heat change. So the resistance of the thermistor changes. The way that it reports signals is based on like the part. So if you have just like a basic thermistor, it's just voltage that you're analyzing via like some type of microcontroller or microprocessor. So it's not necessarily slow. If the device that you're using is slow, yeah, your reporting will be slow. But if it's, you have a basic thermistor, you have a really fast sampling rate on whatever you're using, it can be really fast.
Okay. Yeah, that's a good catch. Since it's an electrical device that senses temperature like pretty much directly, the response, as Des explained, shouldn't be that bad. So the error handling of like a fuse blowing can actually be, you know,
The reason why you would want to look at it for voltage rather than temperature is because the temperature isn't really going to change all too quickly with like a fuse blowing. Like it's not really going to pick that up. Versus if the voltage changes all of a sudden for that 6 parallel segment or like the power output or what have you, that will be noticed like pretty much instantly. Like you would notice it within microseconds. And I don't think that the AMS actually reads that quickly. I think it reads on the order of like a couple of milliseconds. So it will notice pretty much instantly.
Right. Moving on. I explained the isolation relays as well, or the accumulator isolation relays, as the rules call them. You see this like wonky construction of bus bars that we had to create to make sure that power is conducted properly. That's going to take a couple of iterations, honestly, to bend together properly, or we get John to do it, and it works. Or Bailey, actually. Bailey's way better at bending metal than John. Yeah. Did I go over main fuse and everything? Okay, yeah. I explained the benefits of bus bars. Like you can get into tighter spaces with them because the bend radius of zero gauge cable is like massive, right? Bus bars you just bend to 90 degrees, 45 degrees, whatever the hell you want. They're also low resistance. That's a key thing. Low resistance bus bars. Let me backtrack for a second, make sure I didn't miss anything. Any questions on this like isolation relay bus bar construction? Okay. I went over the fan controller. Honestly, the new fan controller does essentially the same thing as this. It takes I2C digital signaling from the VCU, and it turns it into PWM control for each fan. Each fan is basically a brushless DC motor, so that can be controlled by PWM, pulse width modulation, by the fan controller. We made a new fan controller, I believe, specifically because the old one does not have like the amount of power, can't take the amount of power you need to put in these fans.
The problem with the one that you're looking at is that the frequency rate of the PWM controller on it, it's too slow. So it won't control the motors inside of the fans fast enough. So with knowing that, I decided to make a new one. It's more or less the same design methodology, like the idea of it's the same, takes in the I2C, but it has controllers on it that can read at a much faster pace, in which case it can put out a faster PWM signal so it can control those fans a lot better. Plus the controllers on them, they're more advanced, so I can do some really cool things with them.
Right. Yep. I also went over the DC-DC, both of them, and I explained that we're gonna have two in this car: a 400 to 24 volt DC-DC and a 24 volt to 12 DC-DC. Any questions so far? Yeah.
So why is it called a DC to DC converter instead of a transformer?
Because transformers typically convert AC to AC.
Yeah, transformers are devices that convert AC to AC. You don't typically see transformers in a DC application. Like there's some filtering things that you can do with a transformer, but otherwise, no. All you see them for is AC.
So I mentioned these connector banks we have. Three outputs are these banana jacks. We call them the TSMP. And the rules, they're referred to as the tractive system measuring points. It basically is just like a port for the judges to stick I don't know, a multimeter, but to stick a device in and make sure you have 400 volts present at the battery pack. These are just banana jacks wired to the bus bars. And I believe they are wired to the bus bars after the relays for safety. Talked about the HVD a lot. Stands for high voltage disconnect. There's a lot of engineering going on with this connector in particular. There's a slip fit interferencing going on with those like poles there. It's a pretty complex like plastic construction, pretty rugged. Has those like little nubbins on the side so you can latch to it. And I think I've explained to you guys before that it has something called an interlock circuit in it. This thing only outputs power from the battery pack if it also receives 12 volt power from the car's battery, basically the car's low voltage battery. Does that make any sense? That's kind of jumbled. This only outputs the 400 volt power if it gets 12 volt power from something else. It's basically its own relay. but as a connector. Pretty wild. So you guys like, I hope you get a feel for like how many safety mechanisms there are in this thing, in the battery pack alone, not to mention all the like the inertia switch and the other, shutdown circuit components on the car. Yeah, lots and lots of safety. Okay. That was dense. I sputtered through a lot of it. So please, questions about anything? Yeah.
How does the charging look like?
You want to answer, Des? Charging?
So what we are doing is we're having an outboard charger. So mounted onto like a cart, I guess you could call it, is going to be a charger that plugs into the wall and converts like wall voltage to 120 volts AC or 240 volts AC into a 400 volt source that we can plug into the car that can charge. In that entire system is going to be possibly going to be a microcontroller that controls all of that. I haven't decided if that's going to be the case or we're going to use another microcontroller somewhere else. I don't know yet, but that will be a thing. Also, the BMS ropes into that. So with a BMS, one of the primary responsibilities of that is to balance the all of the cells so that they sit at the same voltage. So if you ever actually discharge batteries, what you'll find is that if you're discharging them all at the same time, they can discharge to different rates. So like you could have one cell that sits at like 3.9 volts, while another one could be at 3.85 volts. And as time passes and you cycle the batteries more and more, they can get out of line with each other. And that's just because of chemistry. They're not perfect. They're not ideal cells, so that they're going to end up having different variants based on just like power losses and stuff like that. So what the BMS does is that it balances the cells so that when you discharge them, they'll be around the same point. That's the entire system of the charger, I guess you could say.
Yeah. So we were actually buying this DC charger. We're going to have this system capable for like 240 VAC or 120 VAC. So it's like both types of like power sockets that you have. This is actually going to be one of our intro projects, is having you guys, not all of you, like some of you, having you guys design and build mostly the physical makeup of the charging cart, as well as the electrical makeup of the charging cart. I wanted to go ahead and like, I don't know, just tease these like intro projects because you guys need things to do aside from listening to me talk. One of these projects will be the charging cart. Have some basic requirements here that I'll get into Thursday. This will be like Thursday workshop, is just like introducing these projects and like hopefully just guiding you guys through sketches and things, not even CAD models, not even ECAD or PCB models, just conceptualizing things, But yeah, we're gonna use this like bot charger, couple e-stops, buttons. We want to put tires on the cart because like
Off-roading, maybe.
the damn thing has to go everywhere.
Yeah.
Like I said, you're just gonna get like 12 people sitting on it at some point. Not valid because she's on the floor, but yeah. The other intro projects include the fan control test apparatus. This is the most like pretentious name ever.
Indeed.
And you can tell because I named it. But this will basically just be making sure our fan control can control the fans. Our fan controller can control the fans. So bunch of breadboarding, bunch of wiring. Nothing too complicated in the way of electrical hardware, but a good amount of programming, I would think, and a good amount of electrical setup.
It's not too bad.
Yeah.
It's understanding how to work with a embedded system, and the code as far as like that goes, it's not too bad, but it's a thing.
So accelerator filtering is going to be another project. This is like very CS, or even just like math and statistics, if you want to put it that way. Some of the like early days of KS1E testing got us like accelerator input, right? But the sampling rate of the accelerator sensor is so high that the data ends up looking like this, just noisy as hell, and it at times useless. Usually, even if the data is noisy, you can pick out a trend. Like you can clearly see this is some kind of like standard waveform, just noisy. But we want to like eliminate the noise altogether and make sure we have onboard filtering for our acceleration or our accelerator signal. There are a variety of ways to write filters. You have Kalman filters, you have FFTs, fast Fourier transforms, and you have moving average filters. I think what this project will involve is just, well, it's what Des described here is programming a filter in VS Code for any throttle input, any accelerator input.
It's a CS heavy project. This one actually would require more programming like knowledge than what the fan controller would. If I think about it, yeah, it would actually require more programming knowledge.
Yeah.
So if you're actually wanting a somewhat challenging programming challenge, this would be the one that you would want to look at actually doing.
Yeah, Des has gone and cleaned up our GitHub as well. So for those of you familiar, you guys know what GitHub is? Yeah, Colab software for coding programming. Yeah, clean it up. We'll get you on it. It's not like PDM where it's like at someone's house in a basement on some cryptic server. You have to like knock twice and tell someone the password, and someone's mom opens up and like offline for half the year. It's just there. GitHub's just there.
It's still in setup.
Dynamic.
It should be done once I'm actually done working on a project right now. Once I'm done working on that project, I'll get it finished up and then I'll get whoever wants to actually work on any programming projects in that GitHub.
Right. So 2 more projects. If you guys will bear with me, I know we're a little over time. Shit. Why is this accumulator charging cart?
Oh wait, no, that's right. You never actually made that out.
You updated it. Great.
Yeah.
Anyway, the 2 other projects will be like pretty CAD modeling focused, a little bit 3D printing, a little bit of just like hardware assembly stuff. You guys will be making boxes for a latching circuit, which is basically like a reset circuit, and the BSPD. BSPD is the brake system plausibility device. All these circuits have fancy names. What that circuit basically does is make sure you can't depress the brake accelerate at the same time, and also make sure the compared signals at the accelerator match. The accelerator sensor of the car is actually 2 sensors in one housing, one at 3.3 volts, the other at 5 volts. If they don't match, something's pretty wrong, right? So something's wrong. This comparator circuit, this BSP, shuts down the car. That's it. Yeah, so we're gonna go ahead and introduce these Thursday. I feel like, I don't know, it'll be off the cuff, like how many people are on each project, but I definitely want to determine that beforehand before handing it to you guys. And yeah, I mean, I will let you guys pick whatever you're interested in. These honestly were like the last sort of the dregs of like the design tasks that are left for KS2E. It's like full on manufacturing right now. But it'll be great as an intro for you guys.
For any of these circuits that we have on the car, we'll be able to find out what they're supposed to do if you read the rules for the season.
Who's read the rules?
They've released the 2022 rules.
I looked at it a little bit.
Oh my God, guys, you got a test coming up.
If you read the rules specifically for the e-car portion, they have it divided up to where you can find where everything is pretty easily.
The rules honestly have become like less and less intimidating over time. Like they used to be, I don't even know how many pages, but like 200 plus. Now it's like half that. So rules are not that crazy or involved.
And it's actually really,
Complex.
really useful though, because you learn what the circuits are on the car.
Yeah, I
Like
mean,
what has to be there. You learn what the requirements are. And from there, you can take a look at the schematics that we have for our designs and see what has to.
Yeah, for perspective, we didn't like come up with all these circuits on our own. Like these are like mandated. You have to have a BSPD, you have to have a VCU that does certain things, you have to have pre-charge, discharge, and so on. The rules basically prescribe how to design all the control circuitry for the car. So read them. As far as rules test and subgroup tests goes, Jesse told me that the subgroup leaders just issue the test when they feel like people are ready to receive it. Is that correct? Okay.
Yeah, pretty much.
So I will be giving the rules test next Thursday. Is that fair? You guys think?
So did they have to pass the rules test or stuff?
The subgroup test.
I'm talking about the rules test. Yeah. So I administer the rules test and I administer the subgroup test. Rules test will be like John's written it and made it like mid-level difficulty or whatever.
Yeah, if you read the rules, it's not hard.
Yeah.
Wait, is the rule still that like 145 page thing? That's what I saw.
Yeah.
It's not gonna be like, you know.
Wait, is it 145 for the 2022 one? Hold on. No, it can't be that damn long.
It's not gonna be like, you know, integrate, you better write one line of this.
Yeah. It's like, what's the maximum voltage we can run?
The governing rules.
Yeah. What's the answer, by the way? What's our maximum voltage that we have?
400.
600, actually.
400.
Anyway, yeah, I'll give the rules test next Thursday, and I'll give the subgroup test like the Tuesday or Thursday following. Subgroup test I'm supposed to write. It'll just be like more specific things from the rules from the EV sections. So don't sweat it. Seriously, don't sweat it. Yeah.
You're gonna be open up.
No.
Open internet.
No.
This thing is 140. This is getting longer.
You do know.
All right, cool. Thank you guys. Thanks so much. Gonna let you go, Des. Thanks for
All right,
coming.
cool.
Yeah.
Yep.
Hey, Des, when you coming? When you gonna be here?
When these people stop trying to kill each other.